Hello MIS 411 class. Welcome to Chapter 4, Video 5. This is going to be Part 3 in transforming EER diagrams into relations. In the previous step, we looked at mapping ternary relationships, and now in Step 7, we're going to look at mapping supertype and subtype relationships. Now, supertype and subtype relationship mapping is going to be a little bit dissimilar from some of the previous steps. Despite that, I don't think it's overly complicated, but there are things to pay attention to. So on the screen, we can see a simple example of a supertype-subtype relationship. We have a person supertype. It has a partial specialization and overlap constraint, right? So what are we seeing? We're saying that a person can be a student, a person can be an instructor, a person could be both a student and an instructor, right, because of overlap. And because it's partial specialization, a person could also be neither a student nor an instructor. Let's say a person could be, say, a staff member or something. So in the first step, we're going to, as usual, we're going to take each of the entities we see on the screen, the supertypes and the subtypes, and we're going to convert them into relations, right? And with the added item of the subtype discriminator. As you recall, the subtype discriminator determines when you have a supertype subtype, the discriminator tells you which subtype an entity instance is. And you may also recall that with an overlap constraint, what you have is a composite attribute for the subtype discriminator. So you can see in the original supertype, I have person type, student question mark, instructor question mark, indicating that the person type could be, a student could be yes or no, and instructor could be yes or no. They could both be yes because of overlap. They could both be no because of partial specialization. It could be, a person could be neither a student nor an instructor, right? Or it could be both. So over here you can see the simpler aspects. I've created a student relation based on the student subtype. I created an instructor relation based on the instructor subtype. Now notice what I did for the person type subtype discriminator, right? Because it's composite, as we learned early on, when we were doing these mappings, the composite ends up getting broken out into separate fields, right? And so for person type, student, instructor, I created is student and is instructor fields. And the reason I called them is student and is instructor instead of just student and instructor, well, first of all, we can't put a question mark in a field name in the database. That's not really going to work. And I thought just putting student or instructor here, while you could absolutely do that, by putting is student, it indicates that this is a yes or no field. And if I just put instructor, it might be confusing. You might think that field references maybe an instructor ID or an instructor name. And by putting is in front of it, it's kind of a common convention to indicate that field might just be a true, false, or a yes, no, a Boolean of some sort. So the other thing to note is, as we see in this step, based on the disjointness constraint, that's what I'm basing this is student is instructor on, because it's an overlap, right? Now, if this was a disjointness constraint or disjoint constraint, then I wouldn't need to have multiples. I wouldn't have a composite. I would just have person type, and it would just be an S or an I or something along those lines. And then I would just have one field here, person type, okay? Hopefully that makes sense. If not, reach out to me. Okay, so once I've done that, here's the other departure from what we're used to at this point, is we're going to create an optional one to a mandatory one relationship between each subtype relation and the supertype relation. And also keep in mind that I'm only using two subtypes here. If you had a third subtype, you could absolutely have another subtype down here with the same relationship. Note the cardinality on these relationships. Okay, the subtype side should have an optional one, and the supertype side should have a mandatory one. And this holds true for all the subtypes. Subtype side has an optional one, and the supertype side has a mandatory one. And if you think about it, it makes sense. Let's look at this for a second. Whether you're talking about a disjointness or overlap or total specialization or partial, right? We know that not every of the supertype is going to be a specific subtype, right? Not every person is going to be a student, okay? So if we read this out, we would say that each person may not be a student, or may be a student at most. A person's not going to be two students. One person is not going to be two students, right? Each person may be at most one instructor, or they may be not an instructor at all, right? But every student must be exactly one person. Every instructor must be exactly one person. Hopefully that makes sense. And like I said, this really holds true whether it's optional or, overlap or disjoint. It holds true whether it's total or partial specialization, okay? This would not change for the different completeness constraints or disjointness constraints. And so for the last step, now we need to put primary keys in these new relations, right? All we're going to do here is pretty simple, is we're going to create a foreign key in the subtype, referencing the supertype, right? Person ID references the ID primary key of person, and that foreign key is also going to be the primary key. There's no need to create a separate primary key in this case. The foreign key itself is sufficient. We can see as well down here, kind of this representation, the person ID and instructor references the person ID field. The person ID and student also references the same person ID field. I suspect out of all of the different types of mappings, this one might be the most unusual, maybe complicated. So like I said, reach out to me if you have any questions about how to apply this to your diagrams. So those were the 7 different types of constructs in EERDs that we are mapping to relations. And you know, there seem to be quite a few rules, but there are some patterns that emerge. And so let's talk about those a little bit, particularly around one-to-many relationships. So in a one-to-many relationship, what we're almost always going to do is create a foreign key reference in the child relation or table to the parent relation or table, where the child relation is going to be the one on the many side, the one that has the crow's foot attached, right? And the parent is obviously going to be the one on the one side, so 0, 1, optional 1, or mandatory 1. And so the most basic example of this, the one-to-many problem, is a binary one-to-many problem, right? And so what we can see on the right-hand side of the screen is we have instructor and class. We have one-to-many. Instructor teaches 0 more classes, and each class is taught by one and only one instructor. And so when we transform that into relations or tables, right, all we're really doing is we're going to add the foreign key for instructor ID to the class. Now the class is the child, right, because we can see the crow's foot. That's the many side of the relationship. And the foreign key in the child references the primary key in the parent, as we can see right here. And this really forms the basis of all one-to-many, or just about every one-to-many problem. What we'll see is really the distinction is going to be how the primary key ends up getting set in the child. But let's look at some other problems that can actually be reduced to one-to-many, because not every problem appears to be a binary one-to-many on the surface, but it actually can be transformed into such. So we have multi-valued attributes, right? We talked about that at the very beginning of these steps. And when you have a multi-valued attribute, like here we have major, which was a multi-valued attribute. A student can have, 3 majors. They're computer science, Spanish, and something else, for instance. And I think this was step 1. We would actually create a new relation for that major, right, or for that multi-valued attribute, in this case major, and then we create a one-to-many relationship between them. So again, we have the parent, which is students, on the one side. We have major, which is the child, it's on the many side. And what do we see? We see that there's a foreign key that gets created in the major, in the new relation called a student ID, which references, again, the primary key of the parent, which is the student's ID field. Likewise, we have associative entities, right? And once you actually create an associative entity, what do you end up with? You actually end up with 2 binary one-to-many relationships. A student, here's the parent. The student's on the one side, the enrollment is on the many side, and over here enrollment again is on the many side and class is on the one side. Now the only distinction here, or the difference here, is that enrollment is engaged in 2 one-to-many relationships, but actually that doesn't pose any significant issue. Here what we see is, again, if you just look at them separately, you have student and enrollment, and you have a foreign key in the enrollment, in the child, pointed at student. We have enrollment in class, you have a foreign key in enrollment pointed at class. So again, you can see that in all of these cases, what you have is a foreign key inside of the child relation or table pointed at the parent. So we'll continue on, look at a couple more. A unary relationship, it's only one entity or relation, but it still has the same rules, right? Here we create on the child side, which is instructor, as well as the parent, right? On the child side, we create the instructor ID reference, foreign key, which references the parent, which is also instructor. Ternary relationship. And again, here all we're doing is, instead of the associative entity where we talk about sort of two binary relationships, here we have 3 binary one-to-many relationships. Student to enrollment is one-to-many, term to enrollment is one-to-many, class to enrollment is one-to-many, and what do we end up with? We end up with 3 and 4 in keys in enrollment, 1 to each of them, because enrollment is the child in these cases, right? It's on the many side, and student, term, and class are the parents. And finally, weak entities really is just another classic example of this. This is not that dissimilar from the binary one-to-many as well. The only difference is in binary one-to-many, typically you already have a primary key or an identifier in the weak in the child, and here we don't, right? But fundamentally the same idea. Here again, we have the foreign key in the child pointed at the parent. So what really distinguishes all of these from each other is essentially how the primary key gets set. So let's go back through these a little bit from the beginning. The binary one-to-many, we'll start there. And we'll kind of talk about the 3 different options, right? Just keep in mind that the goal, not the goal, but the purpose of a primary key is to uniquely identify every record in that relation or in that table, right? So it needs to fulfill that purpose, otherwise it's not a primary key. So typically there are going to be 3 different ways that we have a primary key in a relation. And keeping in mind also that we intend to put a primary key in every relation. Like I think I mentioned previously, you don't technically need a primary key in every relation or table, but we are going to put one in every relation or table, and typically it's good practice to do so. So we're going to go ahead and abide by that. So often what you'll have, especially with a strong entity, is it'll have its own primary key already. And if it has its own primary key, like in this binary one-to-many relationship, you don't need to create a new primary key. You would just keep using whatever primary key it has, and you generate the foreign key, and nothing changes, right? Now with a multi-valued attribute, we're actually creating a brand new relation, so of course there's no pre-existing identifier that we can rely on. So we have the foreign key in this new relation pointed at its parent, as we've already discussed. So how do we determine what an appropriate primary key is for this major table? Now keep in mind, what will this have? This will have a combination of the student ID, let's say the student's ID is 1234, as well as the name of the major, like computer science or literature and writing. Now if we took either of those individually and tried to make a primary key out of it, just the student ID for instance, well, what if a student 123 is majoring in 2 things? Is majoring in both computer science as well as Spanish, right? Then that primary key would get violated, right? Because if we only had primary key of student ID, we would see multiple 123s in this table. Likewise, if we try to make a primary key purely out of the major name, computer science or Spanish, that would prevent us from having any more than 1 student majoring in those things, because we couldn't have student ID 123 majoring in Spanish, and as well as student ID 456 majoring in Spanish, because then we would have a repeat of Spanish if that was the only primary key. So in this case, what we're doing is we're creating a natural key, which is a combination, or a composite. It's a composite primary key, but also referred to as a natural key, because it's composed naturally of fields that exist in this table, as opposed to the surrogate keys, which we'll discuss shortly. And so we would have a primary key composed of both student ID and name of the major. And this makes sense because we wouldn't ever need to have 2 rows of the same student majoring in the same thing. There's no point in me saying that student ID 123 is majoring in computer science and student ID 123 is majoring in computer science again, right? Because we already know that. So for that reason, in this case, we could use what's called a natural key. Now here with associative entities, this is where we start getting into a little bit of choice, okay? So with associative entities, again, we can use a natural key composed of the foreign keys. Remember that an associative entity actually arises from a situation where we have a many-to-many relationship between 2 entities, right? And so when we create the associative entity, we don't actually have a pre-existing identifier to rely on. You might recall that often associative entities, or generally, don't have anything underlined because we don't have an identifier. So we need to come up with our own primary key. And in this case, typically what will be sufficient actually is the foreign keys of both other entities can also be the primary key. In some cases, even that's not will not give you a unique row, and so you may need to incorporate other attributes or other fields of the associative entity relation. Or if that became too complex, and again refer to the textbook or earlier in this video when we talked about this, you could also generate a surrogate key, which is where you do not use any of these fields as part of the primary key, and you would simply generate your own unique identifier, usually just a number starting at 1 going to whatever, for each record in this table. And again, this is as much a design decision as it is anything else. So for unary relationships, You already have typically a primary key or identifier, so you don't need to change anything. For ternary relationships, again, this is similar to the associative entities. So again, you have the option of either using the foreign keys as a natural key or generating a surrogate key. And often I think they recommend in a ternary relationship or anything at that level, probably generating a surrogate key, because they could become more and more complex. You know, now you have 3 fields at least required just to make the primary key. And so it might be simpler just to have a surrogate key. And so finally, with a weak entity, again, we have a situation where the original entity did not have an identifier. And as you may recall, again, a weak entity relies on the strong entity in the identifying relationship in order to provide some of the information to uniquely identify a row in the weak entity. So the way we would create a primary key here is through a combination of the foreign key reference to the strong entity in the relationship, as well as typically one or more attributes or fields in the weak entity itself. You know, for instance, here we have a combination of the class ID and section number, where class ID alone or section number alone would not be sufficient to uniquely identify a class section, right? Because you might have multiple section number 1s, right? And they will not be unique in the table unless you also add in the class. So CS 101 section 1 can be in this table, as well as Math 101 section 1, whereas if you only had section number as the primary key, then section 1 there could only be one section 1 in the entire table, regardless of what course it was in. Now with this, as with all of these, sometimes you might have a situation where there's some kind of a natural identifier for the table. Let's say that in the case of sections, there was some value that was recognized by business users, for instance, like in an enrollment section code or something, that uniquely identified the class section. You know, in that situation, it wouldn't be a weak entity to begin with, but let's just say for the sake of argument, in that situation, you could of course use that. And I think I mentioned candidate keys some time ago when we were talking about primary keys. And so really, ultimately, the idea here, again, and I know that I've kind of said this several times already, but it really is a design decision. As long as your primary key satisfies the need to uniquely identify every row within that table, it should work. And so the question of whether to use sort of a natural key, use fields that exist within the table that uniquely identify, or generating your own surrogate key, really, again, is kind of up to you. And there's not a really strong consensus in my understanding about whether one is always, is really superior to the other. Some people generate surrogate keys, some people use natural keys, and some people use a mix. So again, whatever you feel comfortable with, as long as it satisfies the need to really be a primary key. Another pattern that I think we'll see while mapping is the mapping pattern of one-to-one relationships. And it's slightly different than a one-to-many, but in a one-to-one relationship, where we create the foreign key will really depend on the characteristics of the relationship itself. If both sides of the relationship are optional, or both sides are mandatory, it doesn't matter that much which side you place the foreign key reference in. Now, you still will need a foreign key reference. We need some way of interlinking these tables, but it won't really matter as much which side you place them in, wherever makes the most sense to you. Now, if one side is optional and one side is mandatory, as we see on the screen here, an instructor must be assigned one and only one office. Each office may be assigned to an instructor, but also may not be assigned to an instructor, right? So we have an optional and mandatory side. When you have a mix, optional, mandatory, you're going to place the foreign key in the optional side, referencing the mandatory side, as we see here. So pretty straightforward rule. Now some other problems that kind of mimic, that also look like a one-to-one, are a unary one-to-one. So instead of a binary one-to-one, we would have a unary one-to-one. So a person is married to 0 or 1 people at any given moment, and everybody is married to by, I know it's a little bit difficult to say that, but you understand the concept here of this relationship. It's a marriage relationship. You can be married to 0 or 1 people. So it's unary between people. Really, really simple. Obviously, there's only one place to put the foreign key and only one thing to reference from the foreign key. So same as for one-to-many in a unary relationship, you have the foreign key person ID referencing back to the primary key person ID. So now we'll examine the supertype and subtype mapping pattern. As you may recall, or you saw not too long ago in this very same video, when mapping supertype subtype entities to relations, to tables, what you end up with is something like this. Each subtype ends up with its own relation, table, right? And it has a one-to-one relationship with the supertype. So in this case, for instance, we have the person supertype, student and instructor are subtypes, and each of them has the one-to-one relationship. As a consequence of the way this is mapped, we also note that the subtype will have the optional side of the one-to-one relationship, and the supertype will have the mandatory side. Because of this, as we said previously, what we do is we put the foreign key reference in the subtype, referencing the supertype. As noted previously, the foreign key itself will also double as the primary key when you map supertypes and subtypes into relations. So that makes that decision pretty simple. So this concludes all the videos on transforming EER diagrams to relations. Let me know if there are any concepts that you had issues with or any questions you have about these videos or in general. And with that, I will close out here. See you in class.